Going to do our second lecture on Chapter 1. There will be one more lecture on Chapter 1 before we proceed on to Chapter 2. So I'm going to work some problems today, talk about a little bit more theory, but this is going to build directly on the ideas of analysis of trusses and axial loads, and we started talking about normal stress. So we're going to take a look over here at the document camp and continue our discussion. All right, so the first thing, could one of you come over here and close that blind for me, because it's got, do you see my little pearls here? This one right here, over here. Yeah, and just twist it up. If you twist it, yeah, perfect. That'll work. It's still kind of awful. Oh well, it'll be better. Ignore it. Ignore the pearls. All right, so I like to refer to these two equations as the most deceptively easy equations. They're not difficult, but when you look at them on the face of it, they look even easier than they are. One is that sigma, or normal stress, is equal to P over A, force over area. And similarly, tau, which we have to subscript as being the tau average, is equal to V, which is a different kind of a force over an area. The reason that they are deceptively easy is you have to decide, you have to look at the geometry, and the deal is that P has to be perpendicular to A, and that V has to be parallel to A. So you have to do this geometry, and then in terms of analysis, you have to decide which area the force, whether it's a P or a V, is acting upon. All right, so in the case of a normal stress, where we have a structural member, cross-section looks like this, and it's either in tension or compression, it's actually relatively easy, because the area is just whatever is perpendicular to the force in that structural member. So let's do a problem like that so that we can look at something that is pretty straightforward, and then we will move on to something. None of these are terribly complicated. I don't mean to imply that these are terribly complicated problems. It's just that you have to think. The math is, like I had said earlier, in some engineering classes, it's like getting to the math was not that difficult, and once you got to the math was difficult. In this course, it's more or less getting to the math, which is the part that you have to give some thought to. I won't say difficult, you have to think about it. And then the math follows pretty easily. Not easy, well, I'm sorry, I don't mean to use the word easy. It's not, it's just a little bit different emphasis. How's that? Okay, so let's look in our textbook at problem 1.1. We have two, I'll put this up on the thing and then I'll draw it in my, of course, because I draw so much better than your authors do. We have two solid cylinders, A, B, and BC, that are welded together at B and loaded as shown. Knowing that the diameter in one is 30 millimeters and the diameter in two is 50 millimeters, find the average normal stress at the midsection of AB and the midsection of BC. Okay, so to redraw this bar, what I have is some sort of a wall or a restraint on the right-hand side, and I have a larger diameter cylinder that is welded to a smaller diameter cylinder. Now, as you see in the picture, the authors draw what they refer to as a rigid end cap or a weld at this point. And what they're really getting at is that the load is going to be equally distributed across that area. So we're not having to take into account the areal distribution of load. Okay, then we have a 60 kilonewton force pulling on point A, And here on this welded piece, we have 125 twice. So we have 125 kilonewtons pushing here and 125 kilonewtons pushing here. We are further told that the diameter at 1 is 30 millimeters. The diameter at 2 is 50 millimeters. All right. So there are two questions that we need to answer. What is the force? And in two different places, in AB and in BC. And the other is, what is the area? What is the perpendicular area in AB and in BC? Okay. In this case, the areas are quite easy to answer. They're cylinders, so we know we're given a diameter. So the area of AB is equal to pi r squared, or pi d squared over 4. And the area of BC is pi d squared over 4. Now, as a recommendation to you, because we want to come out with units of stress, which are going to be Newton per meter squared, which are pascals, I recommend to you that you find the areas in meters squared. So if it's presented in millimeters squared, I would recommend that you write those as meters and use meters. Okay? So 30 millimeters is 30 times 10 to the minus third meters. So the area here is pi times 30 times 10 to the minus third meters, quantity squared, over 4. And here it's pi times 50 times 10 to the minus third meters squared over 4. Now you can put this in millimeters if you're good at converting back. You remember a millimeter, there are 10 to the third millimeters per meter. So in a meter squared, there's 10 to the third squared, or 10 to the sixth millimeters squared per meter squared. So you just have to remember, and you can convert there, but this is just a recommendation. It's not a set in stone kind of a thing. All right. So if I continue with the area of AB, 30 squared is 900, and times 10 to the minus third is times 10 to the minus sixth meters squared, times pi divided by 4. Now you could use a calculator and pull this off pretty quickly, but you know. So this is going to be pi times 900 divided by 4, which is 450, 225 times 10 to the minus 6 meters squared. Or I could just write this as 225 pi times 10 to the minus 6 meters squared is the area of AB. Now you can just plug this into your calculator. This is roughly, that would be 775, so about 800. Yeah?
Is that on the 50 times 10 to the what?
Minus 6? Minus 3 right here.
That's 3.
Yeah, sorry. Yeah, my handwriting is something to enjoy every day for a new adventure. So area of BC then is pi 50 squared is 2,500 times 10 to the minus 6 meters squared over 4. And I guess I could just write that as 30, 900. Okay, yeah, I was just making sure I have my numbers right. So if I take 2,500 and divide it by 4, I get 6 times 4 is 24, goes in twice, carry over 2, and it's 625 pi times 10 to the minus 6 meters squared. Okay, so those are my two areas. Okay. Now what are my forces? Well, I need to remember here that I could have, when these forces are applied, the force here is going to be different than the force here. And the best technique for finding the forces is similar to what we have done, or it builds on the idea of a method of sections, but I refer to this is not a technical term, but I refer to this as a cutaway view. And what we do is, if you think about it, if we put a cut right here in the middle of this first section, AB, this is point A, and we sliced it through right here, if we have a 60 kilonewton force pulling on it right here, in order for this thing not to move, we're going to have a responsive 60 kilonewton force right here, aren't we? So AB, first of all, the load, or the P in AB, is 60 kilonewtons. And is that in tension or in compression? Is AB being pulled on or pushed on? Yep, absolutely. In tension. Okay? So when we look at AB then, we can do the sigma in AB is equal to, tension is positive. Oh, you can't. There, how's that? Better? Thank you. 60 kilonewtons, positive because it's tension, divided by the cross-sectional area, which I found to be 225 pi times 10 to the minus 6th kilonewton per meter squared. Now remember, a newton per meter squared is a Pascal, so this unit is going to be a kilopascal. And the value is going to be 60 divided by 225 pi, and then 10 to the negative 6 in the denominator becomes 10 to the positive 6 in the numerator. And if you have a calculator, you don't have to mess with the numbers like this. I'm just doing it because, I don't know. I can't even justify why I'm doing it. So 60 divided by 225 divided by pi is 416. 416. 225, that's not right. Let me reduce again. Clear it up. Clear, clear, clear.
Can you pull the page out a little bit?
Absolutely. Like that? Okay. So 60 divided by 225 divided again by pi. That's better. 0.08488 times 10 to the 6th. Okay, now we need to write this in a better form. If we move this over 2, we could say, or we could just move it over 6, and that would be how many pascals it would be? 1, 2, 3, 4, 5, 6, 8, 4, 8, 8, 2 kilopascals. That gets rid of the 10 to the 6th. Okay? Or we could write that as 84.9 kilo times 3 is megapascals. Okay? So that is the force in part AB, or excuse me, the stress, the normal stress tension in portion AB. Okay? Now the next thing we would do, we're not going to do it in this problem, we're just finding the stress, but we would have to determine if the material was capable of handling that kind of stress, whatever this was built out of. So if it was built out of balsa wood, we might need to have a thicker piece of balsa wood, or we may have to upgrade from balsa wood to some sort of a steel product. Okay, and 84.9 is pretty significant. That's a pretty big old number. But then this, a 30 millimeter diameter rod, is quite small. Okay, because they're 25.4 millimeters in an inch. So this is just over an inch, and it's bearing quite a bit of load. Okay, all right. Now let's look at portion BC. We have the diameter and we've calculated the area, but we don't know what the force is. So what we have to do is to do another cutaway, like I described, and decide what the responsive force is here to keep everything in static equilibrium. Okay, so it's a little bit more of a drawing. Here's my cutaway. I have 60 kilonewtons pulling it this way. I have 125 kilonewtons pushing it this way. And I have 125 kilonewtons pushing it this way. So in order for static equilibrium, I'm going to have some sort of a responsive force here that is either going to be a push or a pull. I do not know yet, but I'm going to call that force P. okay, because it's perpendicular. So summation forces x equals 0, negative 60 plus 125 plus 125. The way I have it drawn, minus p is equal to 0. Bring p over to the other side. P then is equal to 250 minus 60, which is 190 kilonewtons. This sign is positive, meaning I have chosen it correctly. So if I were to look at this section BC, what I have is a net force of 190 kilonewtons pushing on it, a responsive force of 190 kilonewtons pushing on it. So first of all, is BC in tension or in compression? It's being squished, right? So what is that? Compression. Very, very good. So sigma in BC is going to be negative 190 kilonewtons divided by the area of BC, which we calculated to be 625 pi times 10 to the minus 6. Okay, meters squared. Okay, so sigma BC is equal to, if I take those numbers, I take 190, divide that by 625, and divide it again by pi. I get 6. That's unusual. Really? That can't be right. I think this calculator's messing with me. Let me try it again. 190 divided by 625 equals, divided, this is better, divided by pi, 3.1416 equals 0.0967659.8 times 10 to the 6th kilonewtons per meter squared, which is kPa. And then once again, this is bad form. So I go 1, 2, 3, 4, 5, 6. And I can say then that sigma in BC is 96766 kilopascals, or 96.7, 96.8 megapascals. And the answer is those are negatives. Okay, so there's two ways that you can write this. You can say sigma AB is positive 84.9 MPa, and that sigma BC is negative 96.8 MPa, or you can say sigma AB is 84.9 MPa in tension, and sigma BC is 96.8 MPa in compression. All right, either one of these is fine, but do not say that sigma BC is negative 96.8 in compression. That's like a double negative, so that would indicate that it's actually in tension, and it would be bad form anyway. So you either say it's tension compression, or you say it's positive negative.
What's that after P?
Right here?
No, between tension and P.
Between I don't see P.
That's an A.
This, oh, right here, right, a megapascal. That's an A, a letter A, sorry. I didn't even know what you were talking about, so I apologize. So A, let's see, might be written like that. Is that better?
Yes.
Okay. Like that. Okay. All right. So do you guys have questions about this? What's that?
I just need to know.
Sure. Okay. No questions? All right. So I will do another type of a problem using this exact same principle. And then I'll assign you a little bit of homework, which I'm going to collect all of the Chapter 1 homework together. So remember, your method of joints, method of sections homework, I think, is due tonight at 11:55. Then I'm going to assign some homework for this, the first part of Chapter 1, but I want you to hang on to that until we're done with Chapter 1, which will be probably one more day, so it'll probably be due Friday or maybe even next Monday. I'm not sure right now. Okay? Yes, ma'am.
I have a question.
Sure.
About homework.
Yeah.
I know you want it scanned.
Yes.
Is there a place on campus that
There is. And will you remind me when I get done with this next part of the lecture, because I called Jessie Watts, who's the computer service tech, and she emailed me and told me some places. I know you can do it at the library, and you can just email it to yourself, which is the easiest way. You can do it in my office as well, and if you'd like to do it in an office, I'll tell the secretary that you're going to do that, because she's careful to make sure that we're not that the students or random people are not abusing the office equipment. But if you'd like to do it in there, I'll tell her that you're going to be doing it. Okay? Yeah.
What's the page before that?
There you go.
from the phone?
Oh, super.
What's it
Christian has the answer.
called? Office ones?
Another thing that people will do, that's perfect, and I didn't know about that, so I'd love to get, what is the name of that app, did you say?
Office
Lens, L-E-N-S? Okay, super. So let's write that on here, Office Lens to scan from your phone. The other thing that some of my students have done, and I have another class I'm teaching business math right now. Some of my students will just take pictures of it from their phone and then put it in a Word document if they have access to Word. So you can take a picture of it and email it to yourself, and then you can put it in a Word document.
Actually, it's an entire PDF scanner, so if you need anything.
This is it, this program. I'm going to give this to my business math students. Thank you so very much. Is that a free app too?
Yeah.
Oh my gosh,
Um,
that is so cool.
It's from Microsoft, but it's not an official Microsoft program. Microsoft employees can develop some software. in their free
Oh,
time.
okay. Super. Thank you, Christian. Yay. All right. Very good. I'm going to put that on my phone too, because there's a lot of times where I would love to do that. So,
Okay, here's a question. You crossed out that 416.
yeah, it was just a bad calculation.
Okay, so is it 0.08488?
Yep, times 10 to the 6th, right? Mm-hmm. So then right here is where I've just done the arithmetic. I've just moved the decimal place to get rid of the 10 to the 6th.
Got it.
Okay, yeah. Good questions. Plus Office Lens. Yay. All right. Okay, here's another, this is the same sort of an idea. I'm going to work problem 1.5, which is an application problem, and we're actually talking about pulling on a bone. And you notice there's a 1200 Newton force, not kilonewton, but 1200 Newton, 1200 Newton, and it's pulling on a bone. And the gauge they're talking about, a strain gauge, is actually something that you'll use a lot. Some of you, now if you go to UW, you will not need to have a lab with this course, but some schools require a lab with this course. So one of the things you do is you measure the tensile and compressive strength using a strain gauge, okay? So that's what they're talking about here. It's just like a spring, and you just load something and you see how hard you can pull on it. So a strain gauge located at point C on the surface of the bone AB indicates that the average normal stress is 3.8 MPa when the bone is subjected to two 1200 Newton forces. Now it says it's subjected to two 1200 Newton forces, which it is, but they're opposing each other, right? So the value of P is 1200, it's not 2400, okay? Assuming the cross-section of the bone at C to be annular and knowing the outside diameter is 25 millimeters, determine the inner diameter. Okay, this is what they're talking about. In tubular goods, like pipes or bones, right, bones, if they're not bird bones, are, well, I think even bird bones are full of amaros, so that all of the structural strength is in a ring like this, okay? And the distance from here to here is often referred to as the OD, or the outer diameter, and the distance from here to here is often referred to as the inner diameter. So if you have a tubular good that's in compression or tension, the only place that bears that load, the important area, is this area. This is referred to the inner diameter. The hollowed out inner diameter is referred to as the annular space. And so the ring that kind of looks like a two-dimensional donut is where all the stress is born, because the inner part is just hollow, okay? And since this is a bone, this hollow part is not actually hollow. It's actually going to be full of marrow, but that marrow is just like a mushy, like, you know, spongy substance, right? So it's not going to bear any of the mass or any of the weight, any of the force, to be exact. All right, so here's some of the things that we're told. We're told that P is 1,200 newtons, and we are told that sigma is 3.80 MPa, and we are further told that the outer diameter is equal to 25 millimeters, and we wish to determine the inner diameter. Okay. All right, so let's build on what we know. We know that sigma in the bone, which is labeled AB, is equal to P over A. We're told that sigma is 3.80. Mega means 10 to the 6th. Pascal, which is Newton per meter squared. We know that P is 1,200 newtons, and we don't know the A. All right? But if we do this calculation, A is going to be equal to 1,200 newtons divided by 3.80 times 10 to the 6th Newton per meter squared. Newtons cancels Newtons. Meter squared in the denominator of the denominator becomes meters squared in the numerator. And so we know that the area that is bearing the strength is 1,200 divided by 3.80 times 10 to the 6th.
Is that 25 millimeters or 2.5 millimeters for the outer diameter?
It's 25 millimeters. Okay. And when I do this, I find that the area that is bearing that stress is, this divided by this is 315.789, which I'm going to carry out a few decimal places. These are not significant, but we're going to do that anyway for now, times 10 to the minus 6, because 10 to the 6 in the denominator becomes 10 to the minus 6 in the numerator. So this is the area that is bearing the stress. Okay, so what am I to do with that? Well, what is the area of this shape? A donut like that is referred to as a torus. Okay, that's actually a three-dimensional term, but that's what a donut is shaped like, is called a torus. T-O-R-U-S, I believe. Anyway, the area is going to be the area of the outside circle minus the area of the inside circle. Right? Makes sense? Do the whole thing, then subtract off the annular space. So that's going to be equal to pi times the OD squared, the outside diameter squared, over 4, minus pi times the inside diameter squared over 4. And as you can see, both terms have a pi and a 4, so we're going to factor them out. It's OD squared minus ID squared. Okay. So I know my OD squared. I know my OD. I do not know my ID, but I know that these two things, that this term is equal to the area. So I can set these two equal to each other, and I can say pi over 4 times OD squared minus ID squared is equal to 315.789 times 10 to the negative 6 meters squared. I can then invert and multiply. So I get OD squared minus ID squared equals this number times 4 over pi. Okay? And take that and multiply it by 4. And then divide it by pi. And that number comes out to be 402.0756. And that is in meters squared. Oh, times 10 to the negative 6, sorry. There. All right. Well, I know what my OD is. Since this is in meters squared, I want to report the OD in meters rather than millimeters. So my OD then would be, millimeters is 10 to the negative third. So 25 times 10 to the negative third meters quantity squared. Now if I bring this term over to this side, I get minus 402.0756 times 10 to the minus 6 meters squared. If I bring this over to the right-hand side, I get equals the inside diameter quantity squared. Okay? So now I have 25 times 10 to the minus third squared, which is 625 times 10 to the negative 6 meters squared minus 402.0756 times 10 to the minus 6 meters squared equals the inside diameter squared. So I have 625 minus 402 is the arithmetic part. 402 point, I carried out some decimal places, which will go away in a minute, 0.0756. And that value, this minus this, is 222.9244 times 10 to the minus 6 meters squared equals the inside diameter squared. So I need to take the square root of this. It's become 10 to the minus third meters squared. Oh, I'm sorry. This is squared, and so when I take the square root, that just becomes meters, doesn't it? So I take this number, and I want the square root of that value. And I have to, there, no, where are you? It doesn't have it. My little calculator, oh, there it is. Doesn't have a little, all right, so it's 14.93. 14.93 times 10 to the minus 3 meters equals the inside diameter. Or if I look at this, this is really 15, and 10 to the minus 3 is millimeters, is equal to the ID. So what that means is the bone looks like this. The outside diameter is 25 millimeters. The inside diameter is 15 millimeters, and the distance from the OD to the OD to ID then is 10 millimeters. And that's how you get that particular reading on the strain gauge. Okay, do you guys have questions for me? Yes. Sure. I'm just going to pull up the Moodle page and post a little homework for you guys while you're thinking. Okay. what is the date? It's the 10th of September. Can you imagine? It's crazy. Okay. One point 3, 1.6.
Is that meters squared or how many meters on that ID?
This
No, on the 14.93 times 10 to the negative m.
meters, just meters, right? Because we started with meters squared,
Okay.
and we took the square root. Mm-hmm.
Thank you.
You bet. Please. And all Chapter 1 homework in a single file after it has all been posted. Okay? All right, so just so that you can see this, I'm going to flip over to the Podium PC again. This is your Moodle page. Get rid of that. Oh, what do you want here? Oh, I didn't want to do that. All right, good thing I put this up. Control C. Let's discard this, and I want to go back. I don't want it to be a file. It's just an activity assignment, and this is going to be called Homework Chapter 1. And then this is not the submit button. This is just, I'm just going to describe it. So you can see that it will just say to keep all of your homework from Chapter 1 in a single file and hand it in, or post it, I should say. Hand it in, that implies post. There, after all of it's been posted. Okay, so I'll change the dates and so forth, but this will just give you that information so that you can look at it, okay? If you want to get started. Okay, what questions do you have for me?
I think we'll drop problems first and change.
That's always a good idea. All right. I should probably rename this because I have homework number 1, so this is going to be called homework number 2, right? So let's go ahead and do that first of all. Homework for homework number 2, because we have number 1, Chapter 1. There we go. That's clearer. Okay, and there's nothing to hand in yet. Okay? All right. So I've posted 3 problems for you to get familiar with these ideas. 2 of them are, let me put this over on the document cam again. 2 of them are very similar to what we have done today. In other words, 1.3, only this is just a cylinder that's being pulled down instead of being pulled across. You do the same analysis by cutaways. And then did I have 1.7? I got to look at this again. Hang on just a second. 1.6. Okay, this one, which is just 2 brass rods. But once again, you need to find the length. Well, the length is ABC is a minimum. That's going to be that's kind of an interesting problem. But the 2 lengths add up to be 100 meters. So you can, let's see, let me read through this problem. 2 brass rods, each of uniform diameter, will be braced together at B to form a non-uniform rod. Knowing that the density of brass is this. Oh, I see. So what they're saying here is this brass rod is hanging under its own weight. Right? So in other words, we have a kilogram per cubic meter. You need to figure out the volumes, which would be the area of the cylinder times the length of each of these, to find out what the mass is going to be. Then you would multiply mass by 9.81 to get the newtons, or the weight, because it's hanging under its own weight. Okay, so once again, you're still using the same equations, P over A, area of a cylinder and so forth, but it's just a little bit more, once again, there's a little bit more involved. When you get to the math, it's not going to be very difficult at all. And the last one, 111, got a truss. You guys know how to do this. You're going to have to do the analysis. You want to find the average normal stress in BE. So the real trick is to find out the tension or compression in BE by doing the analysis like we did for the method of joints or the method of sections. Okay? All right. At that point, I'm going to end the streaming so that this is the end of Lecture 7. And at the end of Lecture 7, if you have any questions, please email me or let me know in some other way, and then we will continue with our discussion in Lecture 8 next time. Thanks.